Here's the first day of 9-3. And the structure of these two lessons, day 1 and day 2, is going to be the same as 9.2. But remember that in 9.2, we were focused on a specific type of sequence. We called it an arithmetic, and we saw that its pattern was based off of addition. Okay, we'll really see the same setup in 9.3, but here's basically what's going on. We're going to look at a sequence and then some sums. We also call those series, remember? For a different type. We call it geometric, and those patterns are based off of multiplication. That's really the only difference. So now, if we were to try to identify if a sequence is based off of a geometric pattern, we'd no longer have D. That was for an arithmetic. We called it the common difference. We have this number that we call R, which you could probably have guessed is short for ratio. We can no longer take the difference of consecutive terms and, we're not interested in looking and seeing that they're the same because they're not going to be. It's if we divide consecutive terms like this, that we're going to get the same ratio every time. We call that common ratio R. Unlike D, its counterpart for arithmetic sequences, we do have a rule about R. It can't be 0. Okay? So it's kind of a rule breaker if that happens and the pattern doesn't really follow the properties of a geometric sequence. So R can't be 0, but you're just looking for your common ratio. All right, so here's a couple just looking at identifying if it's geometric. And again, based on the context that these are. I didn't throw any that aren't, but realistically, you probably should check a couple of terms. This is a nice one to easily see it. There's the second term divided by the first. R is 2. You'd see the same for 8 divided by 4, 16 divided by 8. Second one, the second term is 36. Divide that by 12. You'd get 3. Okay? Same with 108 divided by 36 and 324 divided by 108. Now, I'm only going to check one because, again, I know it's geometric, but fractions, as always, they get a little bit more tedious, but I don't want you to lose sight of the fact that you would check it the exact same way. I need to divide consecutive terms. Need a little room here because I'm going to have to take that bottom fraction and flip that. And then we'd have negative 9 over 3. And R would be negative 1/3. Okay? A little bit more to do with fractions, but it's the same deal that you need to divide consecutive terms. There I did the second divided by the first to figure out your value of R. So we have a formula that's based off of, we'll verify it here in a pretty similar way. Ends up looking a little bit different. Here's the first term. The second term would be, we would get that from taking this common ratio and multiplying by it once. The third term, we would multiply by R twice. Fourth term, you'd multiply by R again. So when I said it would be a little bit similar to an arithmetic, we're going to have this pattern of n minus 1 show up. So first of all, it's going to be very helpful to know where the sequence starts. Okay, we really want to know a sub 1. And then it really becomes how many times do we multiply by r? It would be n minus 1. And you can see up above, right, for that second term, I multiplied by r once. To get the third term, I multiplied by r twice. To get the fourth, I multiplied by r 3 times. All right, so these next few will really be a breeze because they're going to be, again, what we call the nice case. You know the first term in r, and if that's the case, just like with arithmetic patterns, life is pretty good, right? 3 times 2 to the n minus 1. This one just says the first 5, right? So if you put in 1, you get 2 to the 0 power, which is, 1. So you just get 3 like we would want to. 3 times 2. You could say to the 2 minus 1 power, but it's really just the first. That would be 6. And if you really recognize the pattern, you're seeing that you're just multiplying by 2. So a sub 3 would be 12. A sub 4, 24. And then our fifth term, 48. Obviously, if you wanted any particular term in the sequence, you stick that number in for n, and you're good to go. Again, another one that's a pretty nice case, right? I won't even write the general formula. I'll just substitute 15 for n. If we want to find the 15th term, it says this one starts at 20, and then its common ratio is 1.05, and that would be to the 15 minus 1, or 14th power. You'll see a lot of r values like that. That would be like 5, for every time we increase n, if we want 5% growth, this would do that perfectly. Throw that into a calculator. It comes out to be a decimal, but there's your 15th. There's your 15th term. Oh, yet another one here. It's a nice case, right? Still going easy on you. First term is 5. Common ratio is 3. There you go. 5 times 3 to the n minus 1 will get you any term you want. All right, this one asks for the 12th. Go to a calculator and say 5 times 3 to the 11th power. This one is kind of illustrating that if you do have a value of r that's even just 3, the terms of the sequence increase pretty fast. We're almost to 900,000 by term number 12. All right, final example here. No more being nice. I've had it with that. That was 3 ones. That was pretty soft. And of course, by being nice and soft, I'm saying you had examples where you knew the first term in r. And here, this is going to make it harder to find those. So this says to find the 14th term, but you know what? Let's really, if you get the formula, you can find any term, right? So that's what this would really involve, is just finding, the general term. Here's what we've got. It doesn't tell us where it starts, so that was mean. And it doesn't tell us r, which is also mean. And they're doing fractions on us, which is mean. It's all right, though. We're done. It told us the 4th term is 125, and the 10th term is 125 over 64. Okay? That's enough. We can figure it out from there. So I'll go to our formula and say 125 over 64 is a sub 1 times r to the third power. Whoops. Back it up. I lied. Didn't mean to, though. That would be the 10th term, so this r should be raised to the 9th. The 4th term is 125, so that r should be raised to the 3rd. Now this is a little bit funky. We've never done this before, but this will work out nice if we divide these two equations. Now back with arithmetic in section 2, we did something similar, but we subtracted the two equations. Okay, not a coincidence here that when we were doing a pattern based off of addition, that we subtracted, and now that the pattern is based off of multiplication, we divided. Okay, so I just need to do that to all three parts. This is going to be a little bit funky. I'm still working with the fractions because I really want an exact value for r. So we got to work that out here in a minute, that we need to divide those two. A sub 1 is awesome, as a sub 1 divided by a sub 1 is 1. Property of exponents here, same base, and I'm dividing, so I'll subtract those. And we get this, r to the 6th power. So I'm going to have 125 over 64. I can multiply by 125, and those will cancel. This wouldn't be quite as tedious if I wasn't dealing with fractions, but that's all right. And that gives us this. R is the 6th root of 1 over 64. Your calculator button, and I can show you in class, it does have a 6th root button, and I'll show you how to use it. The numbers do coming out pretty nice, and we get that R is a half. So that was good. R was a half. Now let's head back up over here, because that was only half the battle. I'm going to go back to this equation right here. I'm going to say 125. I could go back to either one of the two. Equals a sub 1 times r, which is now a half, to the 3rd power. 1/2 to the 3rd is an 1/8. Could multiply both sides by 8 and get that the first term is 1,000. Okay. Let's put all this together. Any term for this particular sequence could be found using 1,000 times a half to the n minus 1. Okay? So if you wanted the 14th, minus 1 would be 13. At this point, you can see why with the value of r that I got, I really wanted to keep it exact, which is why I dealt with those fractions. Here, not as much. I'm okay to go to a decimal and just say, I'd throw that into a calculator. It's about 0.122. Which makes sense. We started at 1,000, and to get the next term of the sequence, every time we took a half. So the second term would have been 500, third would have been 250, and so on. So by the time we get to the 14th term, it's a pretty small number.